In real analysis, perfectly unbroken, continuous mathematical objects can combine in a way that causes the final result to shatter into a discontinuous function. This occurs when we work with a sequence of functions, an ordered list of distinct equations that all share the same domain. We typically evaluate these sequences by taking fixed vertical slices. By looking at specific x-coordinates, we can track the numerical value the sequence approaches at that single location. It is intuitive to assume that if every individual function in the sequence is continuous, the limit function they approach must also be continuous. To test this, we use the sequence f of n of x equals x to the n, evaluated on the closed interval from 0 to 1. Relying on intuition often obscures the specific ways limits behave. To see why pointwise evaluation fails to preserve continuity, we have to look at how these functions evolve over the entire interval. On this coordinate plane, we map the first functions of the sequence, x, x squared, and x cubed. Progressing through higher powers of n, the curves flatten tightly against the x-axis for coordinates less than 1. Algebraically, raising a fractional value to an infinitely large power causes the value to decay toward 0. However, the behavior changes when we look at the exact boundary coordinate where x equals 1. Regardless of the power n, 1 raised to any power remains exactly 1. This creates a limit function that is 0 for almost the entire domain, but suddenly jumps to 1 at the final point. An unbroken sequence of curves has collapsed into a broken limit function, creating a jump discontinuity. The standard method of evaluating limits point by point across the axis is mathematically too weak to preserve topological structures like continuity. The pointwise convergence definition states, for every x and error-bound epsilon, there must be a threshold index n where sequence functions stay within that bound. In this logic, x is chosen before n, meaning n is a function of both error tolerance and location. Because of this dependency, the sequence is allowed to converge at different speeds depending on which x-coordinate you are evaluating. This creates a loophole that can be exploited by a sliding peak function. As index n increases, the parabola's width shrinks, its base moving toward the y-axis, while its peak stretches exponentially upward out of view. Fixing a single coordinate, like x equals 0.5, the peak eventually slides past it. Once passed, the value stays flat at 0. Since the peak eventually moves past every single x-coordinate, the pointwise limit for the entire domain is 0. This 0 limit ignores the physical reality of the sequence, where the maximum value of the function is actually growing toward infinity. Allowing the threshold n to depend on the location x allows the sequence to lag locally. It permits pathological behaviors to hide from the final limit function. To prevent these local lags, mathematicians required a stricter constraint that completely decouples the threshold index n from the spatial variable x. We can derive this algebraically using the sequence f of n of x equals x over n on the interval from 0 to 1. We start with the standard error inequality for a sequence converging to 0. Since our domain is positive, we can simplify the expression by removing the absolute value bars. By rearranging the variables, we isolate the sequence index n. At this stage, the index n is still dependent on the coordinate x, but we know the maximum possible value of x in this domain is 1. By using this bound, we eliminate the variable x from the requirement entirely. We have now found a threshold for n that works across the entire interval, regardless of your location. This is the definition of uniform convergence. The threshold n now strictly depends only on our error tolerance epsilon. Finding a universal threshold n ensures that the sequence index no longer depends on where we are on the x-axis. The entire function is now forced to converge within the error bound at the same rate. To see what this global constraint looks like geometrically, we can visualize the convergence process. This curve represents our continuous limit function, f of x. We draw parallel lines slightly above and below this function to represent our error bounds. This bounded region is the epsilon tube. In pointwise convergence, curves might sit mostly inside, but sharp spikes are permitted to pierce outside the boundaries. Uniform convergence is stricter. At threshold n, the entire sequence curve must fit neatly inside the tube. This strict requirement for simultaneous entry is exactly what prevents the sliding peaks and lagging behaviors we saw earlier. The epsilon tube is the geometric manifestation of decoupling n from x, enforcing a rigid uniformity across the spatial domain. This resolves the problem we saw with the x to the n sequence, where continuous functions produced a disconnected limit. Structural breaks like that are impossible within an epsilon tube. If every part of the curve is forced to stay close to the limit function at the same time, the limit cannot suddenly disconnect. This leads to a central theorem. If a sequence of continuous functions converges uniformly, the resulting limit function is guaranteed to be continuous. It is important to remember that convergence is a relationship between a formula and its specific domain. While our sequence converged uniformly on the interval from 0 to 1, extending that domain to the infinite real line removes our boundary constraint and destroys that uniformity. In analysis, evaluating a sequence at isolated points often misses the bigger picture. Only uniform convergence provides the global constraint needed to guarantee that properties like continuity are preserved from the sequence to the limit.